Good morning, everyone. Today we are talking about double binary factorization and non-uniform compression heuristics, which is based on reproducing and extending the state-of-art work on double binary factorization, which was recently accepted at Neural IPS 2025. I am Aditya Vardhini, so I am here to give you a brief introduction about the double binary factorization. The central thesis of this research is fundamentally transformative for the field of efficient deep learning. We demonstrate that it is possible to replace the most fundamental atomic operation in neural networks, the floating point multiplication, with simple integer addition. And we can do this without retraining the model from scratch. This is achieved through a novel mathematical factorization technique that decomposes weight matrices into product of binary matrices. To give you context on why this matters, modern LLM models like ChatGPT requires billions of multiply accumulate operations per token. Each floating point multiplication consumes significant energy and requires complex hardware. By converting these operations to additions on binary values, which are plus 1 or minus 1, we can theoretically reduce energy consumption by over 10 times and enable deployment on resource constrained devices. In today's presentation, we will walk you through four key components. First, the mathematical foundation of double binary factorization and the optimization algorithms that make it work. Second, our implementation strategy on small scale models. Third, our novel extinction using sensitivity based non uniform compression. And finally, our experimental results demonstrating the practical viability of this approach. Let's begin by understanding the computational bottleneck that motivates this entire line of research. So, I'm here to discuss the section one, which is the introduction and motivation of this project. Before we dive into the solution of this problem, let's establish exactly what problem we are solving. The challenge of deploying large language models isn't just academic, it's rooted in fundamental physics of computing. First, consider storage. A modern 8 billion parameter model stored in FP16 precision requires 16 gigabytes of memory. The 70 billion parameters variant requires 140 gigabytes. This immediately excludes deployment on consumer hardwares like smartphones, which typically have 14 to 12 GB of RAM. But storage is actually not the hardest constraint. The real bottleneck is memory bandwidth. During text generation, we operate in an autoregressive mode. Each token must be generated sequentially, and for each token, we must load the entire model weights from DRAM to GPU's compute units. Modern GPUs have enormous computational throughput. A100 can perform 312 teraflops, but they're starved by memory bandwidth, which tops out around 2 terabytes per second. This means a lot of time is spent moving data than computing with it. Now let's talk about energy. This table shows the energy cost per operation on a 45 nanometer CMOS process. A 32-bit floating point multiplication cost around 3.7 picojoules in constraint binary XOR operation, which is logically equivalent to addition on binary values, cost less than 0.03 picojoules. That makes 100 times difference around. When you multiply this across billions of operations per interface, the energy saving becomes substantial. Our goal with double binary factorization is to address both problems simultaneously. We want to reduce the model size to approximately 2 bits per weight, achieving a 8x precision ratio, while also converting the majority of floating point multiplication to cheap binary operation. This is dual optimization that makes DBF particularly powerful compared to traditional quantization methods. To appreciate where double binary factorization sits in the landscape, we need to understand the four major paradigms of neural network compression. Each has distinct trade offs in terms of compression ratio, accuracy preservation, and hardware compatibility. The first, scalar quantization. This is most widespread approach used by methods GPTQ and AWQ. The idea is simple. Round each floating point weight to the nearest quantized integer value, typically using 3 or 4 bits. We store a scale factor and 0 point to reconstruct an approximation of the original weight. The problem, while this reduces memory footprint, it does not reduce compute cost. Before we can multiply the quantized weights by activations, we must dequantize them back to FP16. So the matrix multiplication y equal to wx is still performed in floating point arithmetic. We save memory bandwidth but not energy per operation. Second, vector quantization. Methods like uh, QULP and AQLP takes more sophisticated approach. Instead of quantizing individual weights, they group weights into vectors and map each vector to an entry in a learned codebook. This is more expressive than scalar quantization because it can capture correlation between weights. However, the practical language is the codebook lookups introduce indirection and memory latency, which makes this method difficult to deploy efficiently without custom hardware accelerators designed specifically for this access pattern. Third, the extreme binarization. This is where methods like bitnet and one bit operate. The idea is maximally aggressive. Constrain all weight to binary values, either plus 1 or minus 1, or sometimes minus 1, 0, or plus 1 for ternary networks. These methods typically model the weight matrix as W equal to alpha dot sine W, where alpha is a single global or per channel scaling factor. The problem is that this is essentially a rank 1 approximation of the magnitude structure. Real weight matrices have complex heterogeneous magnitude distributions that can be captured by a single scale or vector. As a result, the extreme binarization often leads to catastrophic accuracy degradation, especially on large models. Finally, we have factorization based methods. Traditional approaches like SVD decomposes W into U dot sigma of V power T, which is mathematically elegant but computationally expensive to calculate and doesn't inherently reduce bit width. LoRa factorizes weights, updates for fine tuning, but never compress the base model. Double binary factorization bridges these worlds. It combines the memory efficiency of binarization with the expressiveness of factorization. Instead of a single binary matrix, we use two, A and B, both strictly binary. These are scaled by continuous vectors A, M, B, which captures the magnitude information. The key insight is that the middle dimension K gives us a flexible knob to control compression ratio. We can smoothly trade off between 1 bit and 3 bit equivalent weight, which no other method allows.
So, hello everyone. My name is Parv Agarwal, and now I'm gonna talk about the theoretical framework behind double binary factorization, the mathematical formulations, and the techniques we employ to solve or to work around this double binary factorization method. So, first, let's talk about the mathematical formulation of double binary factorization. This equation appearing on your slide appears to be simple, but encodes a very profound idea. We approximate the original dense matrix W with dimensionality n cross m as the product of two matrices, but the catch is this. The matrices A and B have the constraint that they are strictly binary. That is, they contain values only +1 and -1. Now let me break down each component of the equation. A and B are the binary matrices. A being the with dimensionality n cross k. It captures patterns in the row space of the original weights, while B being dimensionality k cross m captures patterns in the column space of W. The dimension k is what we call the middle dimension or latent dimension. It is analogous to the rank in SVD, but here it is enforced through binarization rather than singular value thresholding. This equation also has three more vectors, A, B, and M. These are the scaling vectors. These are continuous valued with FP16 format for each entry. They handle the magnitude information that the binary matrices cannot express. The vector A scales each row, the B scales column, while M scales the latent factors. The dot operation, which you can see in the equation, is the Hadamard operation, which refers to the element-wise multiplication. So we are scaling the rows of A, columns of B, and latent dimension simultaneously. Now here the thing which makes this equation powerful is the dimension k, which acts as a continuous knob for compression. Modify k, you'll get a different compression value. Unlike traditional quantization method where compression ratios are limited only to discrete bit widths like 2-bit, 3-bit, or 4-bit, you can set k to any integer value and smoothly interpolate between compression ratios. Let me give two examples. If n is equal to k, you get 2 bits per weight. While setting k equal to n by 2, you get approximately 1.5 or 1 bits per weight. The flexibility is unique. Now let us do a quick storage calculation. Now the original matrix W has n cross m entries, each being 16 FP16. So it requires 16 into n into m uh, storage cost, while A and B now working on the RHS. A and B are just binary matrices, so each entry needs just one bit to express. Total entries are nk plus km. For scaling vectors, we need n plus k plus m values in FP16, which gives 16 into n plus k plus m. Hence, the total becomes nk plus km plus 16 into n plus k plus m. Now for a typical n equal to m equal to 4096 and middle dimension equal to 4096, this works out to be roughly 2.1 bits per bit compared to 16 bits for the original FP16 matrix, a compression ratio of about 7.6 times. And the key is that this isn't a lossy rounding, it is a structured factorization that preserves essential geometry as well as magnitude information of the weight matrix. Now let us formulate the optimization problem that which will help us to compute A, B, and the scaling vectors. Now the optimization problem formulation is shown on your screen. We want to minimize the Frobenius norm of the reconstruction error as seen from the equation. Basically, we want our estimated weight matrix to be as close as possible to the original weight matrix. But solving this optimization problem is a very difficult problem because of the following three challenges. First of all, A and B are not real valued continuous matrix. Rather, they have a discrete constraint upon them, that is, they are strictly binary. This turns out to be a combinatorial optimization problem for a matrix of size 4096 cross 4096 with middle dimension k equal to m. We are talking about approximately 50 million binary variables. Hence, the search space is 2 to the power 50 million, which is astronomically large. Secondly, the problem is non-convex. Even if we forget about the binary constraints for a moment, the product of A and B introduces a bilinear term, hence introducing multiple local minima. Standard convex optimization techniques won't follow. Now, the third class of problem is that this is a NP-hard problem. That is, there is no polynomial time algorithm to find the global optimum. Hence, we fall back to heuristic-based approaches. Now, the paper's approach is based on a classical technique known as alternate minimization, also known as block coordinate descent. Here's the institution. Instead of trying to optimize all variables simultaneously, we break the problems into two subproblems. First, we introduce a very clever variable splitting. We write the middle scaling vector m as the element-wise product of two vectors m1 and m2. This allows us to create two symmetric LHS and RHS subproblems. Let us call them scaled A and scaled B. Now, the key trick. We pretend that we know scaled B and we try to solve for scaled A. Then, after finding A, we fix the scaled A and then we solve for scaled B. Now, we detail how to solve each of the subproblem in the next part. But let us analyze this strategy once again. So, typically this converges in 10 to 20 iteration. While this doesn't guarantee the global optimum, empirically it finds a very good local minima that works well for neural network compression. Now, talking about how to solve the subproblem. Given a fixed scaled B, How do we find the best scaled A? This a problem is to minimize the Frobenius norm of AB minus W, subject to the constraint that scaled A should be expressible as shown in the previous slide and scaled B similarly. The representation of scaled A, that is small a dot M transpose, is what we call as SVID fit. To solve it, we employ ADMM, which stands for alternating direction method of multipliers. This algorithm is popular for problems with constraints that are easy to project but hard to optimize, used in computer vision and machine learning. The core idea of ADMM is to introduce an auxiliary variable z that serves as a proxy for scaled A and then add a penalty term that encourages scaled A and z to be close. We augment the Lagrangian with this penalty, controlled by a parameter rho and a dual variable u, which acts like a Lagrange multiplier, keeping track of the violation of the constraint scaled A equal to c. Now, ADMM has three steps through which it cycles through repeatedly. First is the unconstrained minimization. We temporarily ignore the binary constraint and just minimize the augmented Lagrangian with respect to scaled A. This is a quadratic problem and it is a closed form solution involving matrix inversion. The inverse being displayed on in the first circle. Now, this term can be pre-computed and cached for efficiency. This step gives us a proposal matrix W hat that might not satisfy the SVID structure. Step 2 is the projection. We take the unconstrained solution W hat and project it onto the SVID set. This means finding the closest matrix that can be written as A dot capital A dot M transpose. The projection operator is the SVID algorithm, which we will explain in the next slide. Lastly, the dual update step, which tracks the constraint violation thing. We update the dual variable u by adding the residual, which is the difference between unconstrained solution and the projected solution. This update ensures that over iterations, the constraint violation decreases. We repeat these three steps for a fixed number of iterations, typically around 80 to 260 iterations, depending on layered size and desired accuracy. The beauty of ADMM is that each individual step is very relatively cheap and the method is empirically very robust. It converges even when objective is non-convex, which is the case in our scenario. Lastly, let's talk about the SVID projection algorithm. Here, the operator takes a continuous matrix and projects it onto a space of binary factorized matrices. So we take an arbitrary dense matrix C, we extract its structure using the extract signs function, where each entry becomes +1 if it is positive and -1 if it is negative. Then we do the extract magnitude step, where we extract the magnitude information of Z, which is just the absolute value of each element. Now the key step is the rank -1 approximation of matrix capital M, which is based on the idea that in neural networks, weight matrices exhibit low rank structure in the magnitude patterns because different output neurons share similar scales across input channels due to layer norm and batch norm. So representing the magnitude of a rank -1 matrix where row vector captures per output neuron scale known as A and the column vector M captures per latent factor scale is effective. To calculate A and M, we use the method of power iteration, a classical algorithm for computing top singular vectors for a matrix, where we start with a random vector V and repeatedly multiply by M and M transpose, which converges in 5 to 10 iterations, giving us the singular vector A and singular vector M. The final output is shown in the rightmost box, which is A dot Z plus -1 dot M transpose, which is a good approximation for V. This step is computationally cheap because of few matrix vector multiplication and hence the reason why we can call ADMM hundreds of times per year. The elegance of this SVID is that it decomposes a hard combinatorial problem into a combination of a fine extraction and a continuous optimization problem, both of which are well studied.
Important scaling. When we minimize the plain Frobenius norm, we incorrectly treat all weight errors as equally important. But neural networks are heterogeneous. Some weights amplify large activations or sit in high gradient layers. So errors there hurt the model much more. To fix this, the DBF introduces importance scaling using two metrics computed from calibration data, input norm and output gradient. Ideally, we want to minimize the weighted error. Instead of changing the ADMM, we apply a simple trick, rescale the weight matrix before factorization. This inflates important rows and columns. ADMM then treats those entries as high priority automatically. After factorization, we undo the scaling. Result is that ADMM minimizes weighted error on W while believing it's solving the standard problem on W dash. This costs almost nothing computationally and improves perplexity by zero point 0.3 to zero point 0.5, often the difference between incoherent and fluent output. The newer IPS paper proposes a three-stage DBF compression pipeline. Stage 1 performs the layer-wise factorization using ADMM to replace each weight matrix with DBF factors. Stage 2 fine-tunes each transformer block locally by optimizing only the scaling vectors to match the block's original outputs. Stage 3 global PV tuning is full end-to-end distillation using both the dense teacher and the DBF student. It requires approximately 24 hours on 8 A100 GPUs for 50,000 steps, far beyond our resources. For this project, we exclude stage 3. Fortunately, the paper's ablation studies show that stage 1 plus 2 already recover 70 to 80% of the total performance, and stage 3 only adds zero point 0.4 perplexity points approximately. This makes stage 1 and stage 2 sufficient for demonstrating DBF's effectiveness. Our implementation fully supports these two stages. In stage 1, we run ADMM for 260 iterations per layer to produce high quality binary factors. In stage 2, we freeze the binary matrices but keep the continuous scaling vectors trainable. We then optimize these vectors with Adam W to minimize the reconstruction error of each block's output relative to the original dense block. Using only calibration data, this acts as local knowledge distillation. Each block learns to imitate its dense counterpart without full model training because we load and train only one block at a time. Memory usage is low and computation is cheap. OPT 125M block reconstruction completes it under 20 minutes on a single GPU. The final result is a compressed model that preserves most of the original accuracy while remaining fully practical for academic settings without large-scale compute. Code architecture. ADMM factorization implements the full DBF map. SVD Absolute handles the power iteration SVD. Modular design lets us test each step independently. Layers.py is the DBF PyTorch modules. BitLinear stores plus one minus one weights in packed int8 form and unpacks to FP16 for simulated 1-bit GEMM. Mull is element-wise scaling, replaced, rewrites a NN linear into a DBF chain. Compression pipeline. Opt underscore sequential drives layer by layer compression, capture calibration inputs with a hook based catcher, factorize each linear layer, replace it with DBF modules, and then run block wise fine tuning with Adam W. Compress Smart Opt adds sensitivity scoring and per layer K selection. Evaluate.py is the metrics, provides perplexity evaluation, memory speed measurement, FLOPS counting, and plotting utilities. Key engineering choices simulate 1-bit operations in PyTorch, cache calibration stats directly on each module, fully support non-uniform K via the target mid parameter.
Hello, I am Adarsh Gupta and I'll be presenting our proposed extension along with some quantitative results. One of our contributions in this project is extending the original DBF paper with a non-uniform smart compression strategy. The hypothesis is simple. Using the same middle dimension k for every layer is suboptimal. Think about how CNNs work. The first few layers learn very general low-level features and are highly sensitive. In contrast, the deep MLP layers often perform redundant transformations and are essentially overparameterized. You can compress them more aggressively without significant loss. We borrowed an idea from convolutional network tuning. In CNNs, researchers have shown that not all channels contribute equally. You can prune channels with low importance and achieve 2 to 3 times flop reduction with minimal accuracy loss. The standard heuristic for measuring importance is a Taylor expansion. If removing a channel changes the loss by a small amount, that channel is redundant. We adapted this to DBF. Instead of channels in the convolutions, we have dimensions in the middle factorization. Each dimension j in the scaling vector m corresponds to one binary vector in A and one in B. We define the sensitivity of the dimension j as the score of j as the sum of the entire batch of the partial derivative of the loss with respect to fj times mj. This is the first order Taylor approximation of how much the loss would change if we set mj to 0. The gradient del L, partial derivative of L with respect to mj tells us how sensitive the loss is to this dimension, and we square it to make it positive and weight by the current value mj summing over the calibration batch gives us a better estimate. Moving on to the algorithm. First, we run an initial uniform factorization with k equals n for all layers. This gives us a baseline and crucially computes the scaling vector a, m, and b. Then we compute sensitivity Sj for each dimension in each layer by running a forward-backward pass on the calibration data and collecting gradient. Then we aggregate these to a per layer sensitivity score. Next, we rank all the layers in the model by their score values. Next, and this is the key insight, we bin the layers into percentiles. The bottom 30% of the layer's lowest sensitivity get a reduced K of 0.66n, which is about 1.5 bits per weight. The middle 40% keep k equal n's, which is 2 bits per weight. The top 30% highest sensitivity get an increased k of 1.33n, which is 2.5 bits per weight. Finally, we run the factorization with these layer specific k values. Here's a concrete example from our opt 125 million experiment. The input dimension n for most layers is 768. For the first attention's layers theory projection, the sensitivity score was in the top 30%, so we allocated k equals 1024. This gives the layer approximately 2.5 bits per weight. For a middle layer, the sensitivity was average, so we kept k equals 768, which is 2 bits. For a deep layer, the sensitivity was low, so we reduced k to 512, giving 1.5 bits. When you average across all layers in the model, we get 2.1 bits per model, similar as a uniform approach. But because we reallocated bits from insensitive to sensitive layers, the perplexity improved by about 0.5 points. Now moving on to the section 4, which is results, analysis, and conclusion. Talking about our experimental setup, we experimented on two models, the OPT 125 million fine-tuned model on the Wikitext 2, and our second model is Tiny Llama 1.1 billion. For our dataset, we used the Wikitext 2 with 128 samples and sequence 2048. For our hardware, we had a single NVIDIA A100 GPU with 80 GB VRAM for experimentation. But for testing, we also ran on mobile and laptop GPUs. For our compression variants, we tried three variants: the dense FP16 original model, the DBF uniform model in which we fix k equals n for all layers, and DBF smart compression, which we just detailed, in which we have variable k per layer based on the sensitivity. Some implementation details essentially are: we performed 260 iterations of ADMM per layer. We performed 4 epochs of Adam W block-wise fine-tuning, which was stage 2, and the binary matrix is stored in the packed int8 format. Now moving on to the quantitative results on OPT 125 million. So for our model size, the dense FP16 is 230.8 megabytes. Uniform DBF compresses to 92.9 megabytes, which is a 2.48 times reduction. Smart DBF is 93.8 MB. This is more conservative than the 7 to 8 times reported in the paper for 7 billion model, but demonstrates that double binary factorization works on smaller 125 million parameter models. Regarding the perplexity, the dense baseline is 23.06. Uniform DBF degrades to 42.10. This is substantial. However, Smart DBF recovers 0.5 perplexity to reach 41.60, which is 1.2% relative improvement. Why higher perplexity than paper? We thought of two reasons for this. First of all, we skipped stage 3 global distillation, which takes 24 hours on 8 A100 GPUs, which the paper shows recovers 5 to 10 perplexity levels. And the second reason we thought of this is that 125 million models have less redundancy than 7 million models, and therefore much harder to compress without accuracy loss. Regarding the inference speed, the dense model runs at 22 tokens per second. DBF uniform, however, runs at 81.4 tokens per second, which is 3.7 times faster. This is because the DBF model is able to account for the memory bandwidth bottleneck. Since the model is 2.4 times smaller, we load from the DRAM 2.48 times faster. Regarding the flop reduction, we went from a 247.1 to 93.4 megaflop, which is a 2.65x reduction. And with custom binary kernels, this translates to energy savings. Now on the tiny Llama 1.1 billion results, which demonstrate the scalability to billion parameter models. The compression ratio jumps to 4.72x, that is 2.2 GB, to around 428 MB. This is significantly better than OPT's 2.48 times reduction and confirms the paper's finding that larger model compress more effectively due to redundancy in their weight matrices. The perplexity degradation is also much lower. The dense is 6.96 and compressed is 11.06, which is only a 59% compared to OPT's 83%. Large models are therefore more robust to compression. The practical impact of this is that the memory drops from 2109 MB to 478 MB. Dense tiny llama requires 3 plus GB GPU, and however compressed models fits on small GPUs like the GTX 1050 Ti. This demonstrates that billion parameter LLM. This democratizes that billion parameter LLM's access. Regarding the speed, we went from 10.8 token per second to 40.3 token per second, which is 3.7 times faster. Again, memory bandwidth bottleneck dominates, and 4.72 times smaller model is roughly translating to that much less DRAM traffic. Regarding the flop reduction, we went from 2.07 to 0.314 gigaflops, higher than OPT's 2.65 times reduction. Tiny Llama has deeper layers with more matrix multiplication that get replaced by binary ops.
Hello everyone, my name is Abhishek and I'm gonna talk about hardware efficiency and memory analysis of our experiment. So let us analyze the real hardware measurements from our experiment. Memory OPT drops from 252.9 MB to 114.4 MB VRAM, which is 2.21 in X reduction. Breakdown weights 230.8 to 92.9 MB compression. Activations about 22 MB, which is almost unchanged. On Tiny Llama, 2109 to 478 MB, which is 4.4x reduction. Now deployment impact, OPT DBF fits on the 2 GB mobile GPUs, while Tiny Llama DBF runs on 4 GB consumer GPUs. GTX 1050 Ti. Without compression, Tiny Llama needs 3 plus GB, excludes most consumer hardware. Speed. The surprising result, DBF is 3.7x faster in a PyTorch simulation. Why? Memory bandwidth is the bottleneck, not compute. Autoregressive generation loads the entire model from DRAM per token. 2.48x smaller model is equal to 2.48x less PCIe traffic. We unpack binary weights to FP16 on chip, fast SRAM, overhead is negligible. Net massive speed. This is to some extent goes against the paper simulation slowdown. We think difference is recent PyTorch optimized memory patterns and mixed precision reducing data bus traffic. Theoretical potential. With custom CUDA binary GMM kernels, eliminate packing entirely. Binary ops are 10 to 16x cheaper than FP16. Estimate 5-8 times total speed up. Memory plus compute. Energy 70 to 80% reduction because binary operations are run by hundredth energy of FP16 multiply. Critical for battery devices. Model loading, OPT dense 1.16 second, DBF 0.46 second, 2.5x faster cold start. In multi-tenant serving, swapping models per request, this means higher GPU utilization and lower tail latency. Now, talking about the conclusions and key achievements, let us summarize what we accomplished in this project mapped to our original proposal. Proposal goal 1, reproduction. We successfully compressed OPT 125M and about 2.5x compression and validated scalability on Tiny Llama 1.1 billion, 4.72x compression. Core ADMM factorization works. Goal 2, statistic and analysis. We measured PPL, convergence, accuracy metrics, uniform DBF grades, OPT by plus 19 PPL, smart recover 0.5 PPL. Tiny Llama degrades only plus 4.1 PPL. Large models are more robust. Goal 3, hardware analysis. Real measurements: 3.7x inference speedup, 2.21 to 4.1x memory reduction, and 2.65 to 6.59 flops reduction. Goal 4: non-uniform extension. Our smart compression strategy uses Taylor expansion sensitivity metric to allocate bits. Variable k across 72 layers recovers 0.5 perplexity at same average bits as uniform. Key quantitative results: OPT 2.58x compression, tiny lemma 4.72x, PPL degradation plus 18.5 smart versus 4.1. Speed up 3.7x, memory reduction 2.2 to 4.4. Flops reduction 2.65 to 6.59. Novel contribution: smart compression recovers accuracy via sensitivity based allocation. Scalability validated from 125M to 1.1 billion parameters. Hardware efficiency proven: 3.7x speed up without custom kernels. Deployment viability demonstrated. Fits on $150 consumer GPUs. Now some future directions. Extreme compression, that is less than 2 bits per bit. Explore k equal to n by 4, n by 8, n by 16, which is 1.5 to 0.5 bit width. Challenge: ADMM convergence becomes unstable at low k. Global distillation, missing component to close 0.1 to 1 ppl gap. Distilled dbf from fp16 teacher. Expected smart dbf to be near lossless. Some open challenges and future research domains: mixed precision hybrid compression, that is, we combine DBF for insensitive layers plus FP16 FP8 for sensitive layers. Target 2.3 bits per bit with higher accuracy. Compatible with GPTQ, AWQ, smooth quant. Hardware co-designing: build accelerators which are optimized for binary factorization. On-chip 1-bit storage with fused XNOR and pop count units. Potential 10 to 100x efficiency versus GPU. Thank you.